So good afternoon to everyone. Thank you very much to Abraham for introducing me, and thank you very much to Amy for inviting me to give today's talk. So today's talk is about source code obfuscation with evolutionary algorithms. So these are the contents that we are going to cover during this presentation. First of all, I will give a brief introduction about me and my different lines of work. Then we will introduce the motivation of a problem, what is code obfuscation, the different types of code obfuscation techniques that exist in the literature, and what have we done in this line. After that, we will give a brief description about the related works that are in the literature about automatic source.
Louder, please.
What?
Louder.
Okay, thank you.
Outdoor voice.
Okay. So after that, I will give a brief description about the different related works that are in the literature about source code obfuscation. And then we will introduce two different combinatorial optimization problems that are the software obfuscation problem and two-level software obfuscation problem that we have made in this line of work. But we mainly focus in the second one, that is the latest one, and we are going to present some of our latest results in this line. Finally, we will conclude our work and present some lines on future work. So let's start. My name is José Miguel Aragón Jurado. I'm a PhD student in computer engineering department of the University of Cádiz. So I started working in research like I was in my second year of the bachelor degree, I think. I was a student research assistant of Professor Bernabé Dorronsoro, which is now one of my PhD supervisors. And while I was doing my master, I was also working at the same time as a researcher of a national project in Spain. And now in 2023, I obtained the FPU National Fellowship for my PhD studies. That is one of the most competitive fellowships in Spain. So that's all about that. Since 2021, I have been a member of the Gold Research Group in the University of Cádiz. We usually work with AI and mainly meta-heuristic algorithms to solve real-world problems, to design some new kind of algorithms. And my main line of work is about green software optimization. That is about my PhD thesis. So in this line, I have a couple of works in journal, conference, and book chapters. That mainly is about how this uncertainty affects to the evolutionary process when you are trying to optimize software runtime. And in this line, I'm collaborating with Professor Abraham Hindel here at the University of Alberta, as he said before. So I have another line of work that I also work a lot on it, that is about sustainable transport system. We usually work with plug-in hybrid electric buses. So you have like a normal you have a big problem here that when you work with plug-in hybrid electric buses, you need to switch between a combustion engine and electric motor, and you need to know when to switch among them. So we have a couple of works, two journal papers that are, one of them is about offline approach to solve this problem with real-world bus routes from Poland. That basically we use genetic algorithm, multi-objective genetic algorithm to find the best optimal strategy. And then we have another problem that is a dynamic approach to solve that using the deep learning models. Another line that we have some kind of work that it's about video games and artificial intelligence that are also related with software performance. So basically we have a conference paper that it have been presented in June that is about automatic optimization of the Doom video game for Steam Deck. And this talk will be about the last line of work that is source code obfuscation. That is also related in some manner with software performance. So in this line, we have like two conference papers and one journal paper. And the last conference paper is the one where we have defined the two-level software obfuscation problem. So we will discuss this line of work in this talk. So let's begin with it. So nowadays, software plays a crucial role in our society, being the main asset of a large number of IT companies. But this accessibility that today's whole software has presents serious risk. For example, web applications are usually interpreted directly in the client web browser, so users have directly access to the client part of the web application. Also, compiled software applications are vulnerable to different types of attacks, like code tampering or reverse engineering. So when software functionality is exposed, attackers can use this type of information to find another type of vulnerabilities inside the software or even inside the company information system. So to mitigate software vulnerabilities, IT companies are currently allocating large amounts of financial resources to the cybersecurity. So one relevant technique to reduce, not to reduce, more to hide some of the software vulnerabilities is code obfuscation. Obfuscation is defined as like the act of making something less clear or more difficult to understand. So code obfuscation tries to alter and hide some information about the data, the variables, the debugging process, or even alter the instruction flow of the program, making the software more resilient against different types of attack. So let's define what is obfuscation techniques. That it's a really simple concept. And if you have a program P and you apply an obfuscation technique, you obtain the program P prime with some modification or not. But the important part is that the program P prime needs to have the exact semantic behavior that the program P. So there are three different types of code obfuscation techniques that are data obfuscation, which tries to hide information related to the data and variables in the program. We have layered obfuscation, which tries to hide information related usually to the debugging process. And control flow obfuscation, we usually try to alter the instructor flow of the program, making some modification at the control flow graph. So there are several problems with code obfuscation techniques. Usually code obfuscation techniques requires skilled expert with extensive knowledge, not only about the code obfuscation techniques that you are going to apply, but moreover, you need a skilled expert with extensive knowledge of the specific software code that you are trying to obfuscate. So another problem is that there is an open question that is how to measure the obfuscation quality of a program. This is really hard because there is no a clear metric that you can use to measure how much obfuscated is a program. So usually in the literature, there are some kind of metrics that people evaluate. So we take three different complexity metrics of a program in our work that are really simple, but they are used in the literature, that are trigonometric complexity, which basically measure the complexity of a program based on the number of predicates it has. Nested level complexity, which measures the worst case of the nested level complexity that you have in your software, and a more simple metric that is the number of lines in the assembling version of the code. So for work, it's important also to introduce the LLVM compiler infrastructure. This is a widely known compiler infrastructure that basically stands out for its intermediate representation of code. This intermediate representation of code, LLVM, is independent of the programming language and the hardware architecture. So that means that you can change between the front-end part and the back-end part of your compiler pipeline, and you can adapt that part to generate the LLVM from any programming language, and you can generate also the specific output for any hardware architecture. Also, it's really important that they offer to the user a large amount of different code transformation that in this case are kernel bases. These are the typical code transformation that compilers like CLAN has in O1, O2, O3 optimization flags. But you can apply in any order and any amount of transformation that you want, and they are applied into the LLVM IR. So this is an example for how can you make like the LLVM IR for a C software. You can use, for example, the compiler CLAN and meet the LLVM, and then you can apply with the LLVM optimizer some kind of transformation, and you obtain this, the LLVM IR modified with that transformation. And also, it is important to mention that this program maintains the exact semantic behavior. So another tool that we have used in this work is the Tigris obfuscator, which is a classic obfuscator for C programming language. So it takes as an input a C software program and gives you as an output another C software program after some kind of obfuscation techniques have been applied. So for example, here you have the program P and you have the program P prime. And in the middle, Tigris obfuscator have made some kind of flatten, encode, arithmetic, and virtualize operation to the program P to make the program P prime. It's important also that most of the transformation that are here, that are code obfuscation techniques, also maintains the semantic behavior of the program. So the last concept that we are going to use in this work is evolutionary algorithm. That the evolutionary algorithm is a generic population-based meta-heuristic optimization algorithm that are inspired by the biological evolution process. So more specific, we are going to use genetic algorithms that are a subset of this family of algorithms that basically they are individuals of the population that are our solution to our problem, are encoded using a genetic representation. And we have a population of this individual that continuously evolve through selection, crossover, mutation, and recombination until some kind of stop criterion is satisfied. So more important, we are going to use a specific type of genetic algorithm, which is the cellular genetic algorithm, that in this case, the population is structured in a toroidal grid. So this type of algorithm introduced the concept of distance between solutions. So we are not going to cross over a solution with any kind of solution in the population. We're going to cross over our solution only with solution in its neighborhood. So it is known that generally this type of algorithm usually maintains the diversity for longer runs because you have like this concept of distance. So it's a good algorithm to deal with the premature convergence problem when you have like a population that so easy converts to a solution. So it's really useful when you work with real world problems. So finally, using Tigris obfuscation techniques, LLVM bases, evolutionary algorithms, we have defined in our previous work and solved multiple combinatorial optimization problems for the software obfuscation. So we have the first software obfuscation problem that we have defined first in our first conference paper and later extended in the journal paper. And we have the two-level software obfuscation problem that is a new combinatorial optimization problem from our last work. So let's start talking about the related works. So most of the related works in the literature, usually for code obfuscation, use genetic programming. Genetic programming is another family of evolutionary algorithms whose individuals, instead of have genetic encoding, they are encoded in a strict structure. Typically, when you are trying to obfuscate the code, they use the abstract syntax tree as individuals in the population, and they undergo, they usually alter this tree with some kind of operation until some kind of stop criterion is satisfied, and then you have your output result with your software obfuscate. There's a critical drawback in this type of algorithms, and is that they cannot guarantee that the semantic behavior of the program is the same. So you need to apply some kind of additional tests and additional algorithms to check that the semantic behavior of your obfuscated program is the same that the original program. So there are also another words that use LLVM compiler infrastructure for obfuscation. That they usually use the open source project Obfuscator LLVM, that they basically define some kind of code obfuscation technique and introduce them like code generic transformation inside the LLVM infrastructure. There is a recent work from this year from Ahmed et al. That they use like a similar concept that the one that we are going to talk about here. So they make clusters of LLVM transformation using a micron approach. They obfuscate using this combination of clusters, different software programs for the events, and evaluate multiple obfuscation quality metrics. So let's start with the software obfuscation problem. So we have, as we said before, we have previously defined this problem in the conference paper and extended later in the journal paper. So in this problem, basically, we have a unique set of generic code transformation, and each code transformation has a unique identifier. So our individual will be composed of a sequence of numbers, each number representing a code transformation and unique code transformation. Also, to evaluate the obfuscation of a program, we are going to apply this sequence of code transformation into the program, and we are going to evaluate the obfuscation metric selected in the resulting program. So it's really important that the sequence has the different transformation that we are going to apply, represented by numbers, and also it's really important that the order that the numbers appears in the sequence is in the order that the different transformations are going to be applied. This is because the impact of the different transformation in the software is not is really differ among different solutions, not only with the kind of transformation that you apply, but also in the different order that you apply the transformation. So you need to find the best sequence of transformation, what transformation to make, and also in which order are you going to apply that transformation. So our goal of our optimization combinatorial problem is to find that sequence of code transformation that obtain the maximum obfuscation quality metrics. We have also made an obfuscation multi-objective definition of this problem. So we are trying to find the best the set of best sequence, because when you are in a multi-objective problem, you are not going to find only one solution. You are going to find multiple solutions that are pseudo-optimals. So for this case, we are trying not only to maximize the obfuscation quality metric, but also trying to reduce the runtime of the program that we are going to obfuscate. So this is the multi-objective definition. And for this case, we have employed like an evolutionary algorithm with the LLVM infrastructure in the version 9.0.1 with 87 transformation. And we applied this transformation to the intermediate representation of code level. So we are obfuscating at this level of the part of the code. So making a summary of the different contributions of this work, because we are going to mainly explain the results of the last work. We have presented this novel optimization problem. We have applied a multi-objective cellular genetic algorithm for the multi-objective definition, a cellular genetic algorithm for the single objective definition. We have obfuscated 5 software programs of the literature, considering 3 different obfuscation quality metrics. A brief summary of the results. We have obtained highly obfuscated code without penalizing its performance. And also we have find some exceptional case where we can obfuscate the code and also increase the performance of the software, meaning that we are reducing the runtime of the code at the same time that we are obfuscating it. So the last work is about the two-level software obfuscation problem. Yeah.
A simple example. I heard the word you described. Give a little example. Sure, this is original code. This is obscure code. So you see type of transformations.
Well, I cannot show a sample now, but yeah, it's usually you have like some kind of tab instruction, some kind of usually introduce like some conditional flows that usually does nothing. So it, so in, yeah.
You're happy here. Go on.
Yeah. Any questions? Okay. So the two-level software obfuscation problem was presented this month in the IEEE World Congress on Computational Intelligence. So until now, the proceedings have not been published, so I don't have access to the paper. And in this case, we have not only one set of transformation, we have two different sets of transformation. One set of obfuscation of transformation that is going to obfuscate the code at a first level. And we have another set of generic code transformation that is going to obfuscate the code at a second level. So the thing here is that we need to find not only one sequence, but both sequences that are going to maximize the obfuscation quality metric selected for the given software. So we have a two-step solution here because the result of the second sequence really depends in the result of the first sequence, because we apply the first sequence transformation to obfuscate the software, and in this obfuscated software, apply the second one in a second level. So this highly restricts the search space and is also really more difficult to find solutions. So here in this case, we have the Tigris obfuscator with his own set of obfuscation techniques that is going to be applied in the first level at the C source code level. After that, this resulting obfuscated C software is going to be obfuscated at the intermediate representation of LLVM level. So we have this two-level obfuscation method. So the important thing here is that we have the two level, and the second level is dependent of the result of the first level. So to solve this, we propose to use like a more complicated genetic algorithm that is a cooperative evolutionary algorithm that basically we propose to split the search space. We propose to split all variables of individuals into two subpopulations, two islands. First island is going to optimize the variables of the Tigris sequence of transformations, and the second island is going to optimize the LVM sequence of bases. So each island is going to implement the cellular genetic algorithm that, to the best of our knowledge, was the first time that the cellular genetic algorithm was used in a cooperative evolutionary algorithm. So to evaluate one island as solution needs to compose a whole solution of the problem. So to make that possible, at the end of each generation, island is going to share its best partial solution to another one, in order that when you are going to evaluate the Tigris sequence, you are going to compose this sequence with the best one of the latest generation of the another island, and then you are going to evaluate your solution to the problem. So talking about the experimental setting for this work, we use like Python 3 and JMetalPy library to implement the different genetic algorithms. It's important to mention that we have different length for the different sequence that we have. We have 100 length for Tigris sequence and 300 length for LLVM sequence. This means that our individual will be composed of 100 of transformation for Tigris and 300 transformation for LLVM. This is the number of LLVM is because usually O3 optimization flag usually have like 287 over that number of transformations, so it's really similar. Also, it's important to mention that we have two different subpopulations, and also we use like mutation operator. When we are going to mutate one variable of an individual, we change that transformation from another one of the set randomly. So the software program that we have used to obfuscate, we have employed Polybench and Mindbird. Mindbird is from the BIP's benchmark suite, and Polybench has been using a lot of different publications in the literature. And we have also obfuscated these two problems in the previous problem that I told before that was software obfuscation problem. So we can compare our results with our previous work. And we have also obfuscated the office string search, that is a benchmark inside the Thebench suite that has been used in the method related work. So we also can compare for this specific case how works of obfuscation methodology for these three benchmarks, and we compare our results with the related works. So first of all, before talking about the improvement that we have obtained in each metric, these are the values of the different obfuscation quality metrics for each case study. So as we can see, we have like more complex program in number of lines and in cyclomatic complexity. But for example, Mindbird has more nesting level complexity. So we have some kind of different software. And now we are going to see how much we can increment, how much we can improve these metrics using our obfuscation methodology. It's important to mention that each genetic algorithm, we have one genetic algorithm for each case. It means that we run a evolutionary cooperative algorithm to optimize the assembly lines of code for Polybench, another one for cyclomatic complexity with Polybench, another one, and that's all. So to mitigate also the stochastic component, for each case, we have made 10 independent runs, and we have taken the best result of these runs as the best result obtained. So these are the improvement in the different obfuscation metrics that we have that are ranging from a 900% in cyclomatic complexity to 6 million% in nested level complexity for Mindbird. So we have significant improvements in this part. Also, the big question is, we are only considering the obfuscation quality metrics, how much the runtime of the software is worse. So analyzing the solution, usually when the solution that usually have like 60 million% is nested level complexity is like 100% worse in runtime or 150% worse in runtime. It's a bit worse in runtime, obviously. We have a lot of increase in the different metrics, but it's not so big because it was about 0.1 and it passed the seconds of runtime, so it passed like a 0.2, 0.3 seconds. It's a big worsening in the runtime, but you need to study other different cases, and we have as future work to also consider the multi-objective definition and take into account the runtime, just in case we can find also some solution that also improve the runtime and the obfuscation at the same time. So these are the evolution over the number of generations of the best fitness, the worst fitness, and the average fitness. These are for Polybench. The other software have representative plots of this one. So you have a steady improvement over the number of generations for the average fitness, and also you have like high levels of diversity at the end of the run of the algorithm. That means that maybe we can obtain also better results if we continue to evaluate if we make longer runs of the algorithm. And now we are going to compare results with those obtained in the literature. First of all, we are going to compare with the results of Methodol. So as we can see, for events, we have obtained significant improvement with respect to those obtained in the paper of Methodol. And when we talk about our previous work, it's interesting that for Mindbird, we have significant improvement in all cases for the different obfuscation quality metrics. But for Polybench, we have only improved our previous results in cyclomatic complexity. That the curious part of this is that when you try only to obfuscate the code using the LLVM code transformation, it was really hard to increase the cyclomatic complexity. So when we include this two-level solution, it was more easy to increase the cyclomatic complexity using the Tigres obfuscation techniques. So we have improved in this part, but the results obtained in the other parts, in the assembly lines of code and nested level complexity, was much better in our previous work that only used LLVM. That here, it's because it highlights the difficulty of this problem that highly depends of the specific software that we are trying to obfuscate. And as conclusions, we have presented two different optimization combinatorial problems, software obfuscation problem, two-level software obfuscation problem. We have proposed cooperative co-evolutionary cellular genetic algorithm to solve this new problem, and we have studied and obfuscated different software of the literature, considering different obfuscation quality metrics. We have increased the obfuscation levels of the original programs up to 6 million% in the best case, and we have outperformed in the best case the relative words like 400 times. But we have some more studies to do with this. We are thinking about extending our study to large number of software programs, also consider more software obfuscation quality metrics. Also we are thinking about making multi-objective definition of this new problem, the two-level software obfuscation, considering the runtime, considering also energy consumption, considering also different metrics at the same time. And also we are considering about define and implement new source code transformation and include them into the obfuscation methodology. So we have like a lot of work to do with this that is really dependent and really hard to do because we also need a lot of time. So this is all. So thank you very much for your attention. You can ask any question that you have. So you have also my mail if you want to ask something. So thank you very much.
The size of the programs you've been able to obscure?
The size?
How many lines of code?
Yeah. So it was about 6,000 for polybench, 1,000 for MindBear, 600 for the program that we select from Cbench.
Something like that.
In our previous work, we have also like more simple programs that was like less lines. It was more difficult to obfuscate that program than the complicated one because you have like less code to play with it. Yep.
So you obfuscate the program, does it affect the program's performance?
How to?
It's like, does it affect this, how the program runs, how fast it takes to load up?
Yeah, we usually measure how fast the program takes to end. So yeah, we measure the runtime.
So does it change with obfuscation?
Yeah, it depends on the case. So when we are not considering the runtime as an objective in the problem, usually it gets worse, but it depends also on how much worse it gets. We have solution that only gets like 20% worse, but also solution that gets like 150% worse. So it depends on it. Also, I think that in our previous work, we have some case that really goes worse because we use like, in our previous work, we use like the simple problem without two levels with one sequence. And we use like the single objective one and the multi-objective one. So the single objective one usually tends to get like really worse runtimes using that view. So yeah, but usually not that much. But I mean, if you maybe make like a really long run of the algorithm and you take like 1 million of evaluation and you keep struggling trying to improve the obfuscation, maybe you get a really worse time. So for that, it's also important to take into account the runtime as an objective optimization. Yep.
Can you give me an example of how your heuristic function works? Like you have mentioned it, but it just had a name. So
Yeah.
how's it evaluating a candidate?
Yeah, sure. So we have our software program. We apply the different transformation, and we usually measure the different metrics that I introduced at the first. That was like this one. So we usually, for example, for the cyclomatic complexity and nested level complexity, we build the control flow graph and measure the value.
So it's like the measurement of these three things
Yeah.
multiplied together with coefficients or added together.
Yep. Yep.
So have you tried de-obfuscated code?
Have you tried?
De-obfuscated.
Yeah, it was also a line of work that we are trying to apply. We think about making the exact opposite process, making the same, but for the opposite objective. So yeah, we have not tried yet, but it's in our mind. Yeah.
So in your field, does output program size not have or it's not something like a score or
Do you mean output program size? You mean
generated program?
yeah, the size.
So optimizing for that.
So usually when we take into account the lines of code, usually the program size is going to be bigger. So we have not taken into account like we need to find less bigger programs. It's also a good point to change to figure how much we can increase maybe another metric, and we can also make program with less size. But yeah, we haven't considered. We have only considered to increase that program size. But yeah, it's true that if you have a big program size, it will be like strange, have more computationally cost.
Great. Thank you so much. That was really interesting.
Thank you.